Okay, good afternoon, everyone. Before we get started, let me remind you, I'm looking for someone to be the class rep for this class. So if you want to be the class rep, please send me an email. Okay. I posted a video about kind of the example we were doing on Friday. Okay, so you can, it's kind of like a correction or something. So you can check it out if you want. Okay. So today we're just going to talk about, we're going to start talking about commutators and conjugates. Okay. If you have the notes, that would be like section 3. Okay. So we have some idea of the different groups we might encounter, and now we just want to kind of we want to study groups in an abstract way, and then at the same time apply our reasoning to like specific examples. Okay. First of all, we define what a conjugate is. Definition. G is a group. G is an element of G. And X is also an element of G. So the conjugate of X by G is defined to be GX G inverse. Then if H is a subgroup of G, the conjugate of H is just the same thing, but with a whole subgroup. And that would be the set of all things like GH, G inverse, where H is an element of H. So right, the conjugate has we've already seen it has some relation to whether a subgroup is normal or not. So you can I'll just recall that. Recall H is normal in G if and only if GH G inverse is contained in H for all G. Okay. So conjugation has some kind of relation to normal subgroups. Okay. Conjugation is also a way to get a homomorphism. That's the statement of the next proposition. Okay, again, G is a group, and G is an element of G. Then define this function from G to G, which sends an element of the group to its conjugate by G. Okay. And with this definition, then phi G is an isomorphism. Okay, it is one-to-one and onto and an homomorphism. Not only that, but we also have this formula. If we compose phi G with phi H, we just get phi GH. Okay. Let's see why is phi G a let's see why it's a homomorphism. And let's see why this formula holds. Okay, so let's prove it's a homomorphism. So let G be fixed. Let X and Y be in G. Then phi G of XY, well, that's just GXY, G inverse. Well, that's just G, X, G inverse G, Y, G inverse. Because we just sneak in the identity in the middle, and the identity is just G inverse G. Then if we just rearrange the necessary brackets, we see that this is really just phi G of X times phi G of Y. Okay, so that proves that phi G is a homomorphism. Now let's prove this formula. That so this says first conjugate by H, then conjugate by G. That's the same as conjugating by GH. Let's prove that. Right. So let X be in G. Let G and H and G be fixed. And we just want to show, what we want to show is that phi G of phi H of X equals phi GH of X. Let me try and write bigger, just in case. We want to show this. If we can do this for all the elements of G, for all the X's in G, then phi G of phi H equals phi GH, which would be the usual thing. Okay, so phi G of phi H of X, well, that's just phi G of phi H of X. Well, that's just phi G of HX H inverse. Well, that's just GH XH inverse G inverse. Now I need to rearrange my brackets using associativity. And now I just remember that the inverse of, so the inverse of GH is just H inverse G inverse. So this is really GH X times GH inverse. And here we use the fact that GH inverse equals H inverse G inverse. Okay, and now you can see that is just phi GH of X. Okay, so phi G of phi H is equal to phi GH as required. Okay, and in particular, this tells us that a few things. Note that phi of the identity of X is just EX, the inverse is just X. So phi E is the identity map on G. The identity function from G to G. So therefore, that tells us that phi G of phi G inverse is phi E, which is the identity function on G. So therefore, the inverse of phi G is phi G inverse. Oops, I went down too far, but that's okay. Right, so proving this formula allows us to say that phi G has an inverse. The inverse of phi G is just phi G in the phi of G inverse. Okay, in particular, phi G is like one-to-one and onto it is an isomorphism. Okay, and then as a corollary, phi G from H to GH inverse is also an isomorphism. Just restrict conjugation from the elements of H to the conjugate of H to get an isomorphism. Okay, and there's actually more we could say. I mean, this property tells us that, in fact, you get, I don't want to mention it too much, but in fact, you get a map from G to the symmetric group on G given by mapping G to phi G. Okay, this is actually a homomorphism too. But I only wanted to mention that in passing. We'll come back to it. The important thing about this kind of thing is this idea that yeah, that you can do lots of tricks involving conjugation. Okay, we also need to know about commutators. And a commutator is basically a way that we test if two things commute. So the G and H, B and G, then the commutator. Of GH, it's denoted with these square brackets, and it's defined by commutator of G and H is just GH, G inverse, H inverse. Okay, So just a quick fact, just a quick proposition, and that is that GH is just commutator of GH times HG. And the proof, well, it's really quick. So that's why I just left it to the end of the page, I guess, right? Look at commutator of G and H times HG. That's just GH, G inverse H inverse, HG. Now the H's cancel, you get GH, G inverse G, you get GH, right? Okay, so if you want to switch H and G, you can do so, but you get this extra commutator term. Okay. So that tells you that, well, when is GH equals HG? Well, it's exactly when this commutator term is the identity. So we can say, just a quick note, GH equals HG, if and only if commutator of G and H is the identity. Okay. Another thing we need to do is sometimes we want to take the commutator of like subsets. So we need another definition. This is of the commutator subgroup. So let A and B be subsets of G, then define the commutator of A and B by the symbol square brackets. Okay, but it doesn't really make sense to just do the set of all commutators. But what we can do is take the set of all the commutators and find the group that they generate. Okay. So take all the commutators where the first entry is in A and the second entry is in B, throw them all together and let them generate a group, a subgroup of G, and then that's called the commutator of A and B. Then we also have a special case of this. Define the commutator subgroup G prime by G prime is just the commutator of G with G. It's just a subgroup generated by all the commutators of G and H, where G and H are in G. Okay. The commutator is pretty special. It kind of measures how far away your group is from being abelian. Okay. What do I mean by that? Well, we just have a quick example. G prime is the trivial group if and only if G is abelian. Okay. Let's try and just see how to do that. So in this example is to prove the statement, solution. Suppose G prime is trivial. Well, all that means is that whenever you take a commutator of two things, you get E. Okay. But we saw above here that if the commutator is trivial for G and H, that means GH equals HG. So that means that GH equals HG for all H and G in G, and this is the definition of what it means for a group to be abelian. So G is abelian. The end. Okay. We can also compute the commutators of so first of all, any abelian group has trivial commutator. We can kind of see examples of groups where the commutator is non-trivial. Okay, one example. Remember is D4. D4 is the group generated by A and B, subject to A to the fourth is B squared is the identity, and BA is A cubed B. Okay, now to compute the commutator of D4, we need to compute D4 prime. The reason being we want to see like this kind of relation means that D4 is not abelian, but it's like all next door to being abelian. So we kind of want to compute the commutator subgroup to kind of verify that, I guess. Okay. So in fact, D4 prime is just going to be generated by the commutator of the two generators. And that's generated by, so the commutator of A and B is A, B, A inverse, B inverse, and AB, A inverse, B inverse. Well, A inverse is A cubed. B inverse is B. A cubed B is BA. A BBA, well, BB is just the identity. You get A squared. Okay, I did kind of skip a part, and that is, why should the commutator subgroup be generated by, why do I only have to look at the commutator of the two generators? It's because if we look at the commutator of xy with z, this is some complicated thing. So what is this? This is like, actually it's better if I just do it by example for D4. Yeah, that is easier to me. So if you compute, like, for example, a to the I commutator with a to the j b, or let's compute the commutator of a with a to the j b, what do you get? You get a to the j b, then you get a inverse a to the j b inverse. Okay, I'll continue on the next page. But basically, B will write B A inverse will just be is just AB. Okay. So let's rewrite where we ended off and just keep computing. We have a to the JB, and we have A inverse, a to the JB inverse. Okay, so now if we have that BA inverse is just AB, so we have A to the J, AB, and then A to the J B inverse is just B inverse, A to the minus J. Now B times B inverse is just the identity. A to the J times A to the minus J is the identity. You just have A squared. Okay. And then we can try one more example just to see what happens. Let's try the commutator of AB with B and see what happens, just B. Okay, well, that's just AB, B times AB inverse, B inverse. Okay, B times B is just the identity, so we have AB inverse is B inverse A inverse. Here we have B inverse. And of course, B inverse is equal to B, so we have AB, A inverse, B inverse, which is a commutator of A and B, which is A squared. Okay, and if you go through all the different possibilities, you'll find that, in fact, D4 prime is just generated by A squared. So that's a subgroup that looks like E with A squared sitting inside all of D4, which remember is like A squared, A cubed, B, AB, A squared B, A cubed B. Okay, so that's just an example of computing the commutator subgroup. Okay. So, and we kind of think of it like everything in D4 commutes except up to this factor of A squared. Okay, and in fact, if you look at D4 mod the commutator of D4, well, that's the group generated by A and B, subject to the same relations as D4, subject also to BA equals A cubed B. And then once we model by D4, the commutator of D4, well, that commutator of D4 is generated by A squared. So we have the additional relation that A squared is the identity. Now, if A squared is the identity, these other two relations can be simplified. Well, if A squared is the identity, we can forget, we don't have to put A to the fourth equals the identity. So we have A squared equals B squared equals E. And if A squared is the identity, A cubed is really just A. So we have BA equals AB. Okay. And we had another name for this group. This is a commutative group with 4 elements where the square of every element is the identity. We call this is isomorphic to V. If you want to put it like that. Okay, so when we take the quotient by the commutator subgroup, we get an abelian group. Okay. So let us now take just a quick 5-minute break. And we want to explain the relationship between the commutator subgroup and like the quotient, this quotient. Okay. So what we want is that we want to prove like G mod G prime is abelian. That's when we come back. Okay. So I'm gonna end the meeting and just restart it.